Last time we started talking about dynamic routing protocols, and there really are only 3, and I'm considering RIP v1 and RIP v2 as a protocol. There are some differences, obviously, between version 2 and version 1, but generally they work the same way. It's a distance vector protocol. What we want to talk about today are 2 of the other dynamic routing protocols, EIGRP and OSPF. They're similar, but they're different. We'll do EIGRP first because he did EIGRP first in OSPF. EIGRP is a proprietary protocol. It's the one that, if you have all Cisco devices, the one you're probably going to want to use. And the question comes up, why do we have all these protocols? Well, it depends on your environment. We saw that RIP can take an awful lot of time to converge if you've got more than probably 3 or 4 routers, depending on how they're configured, because with the 30-second broadcasts its entire route table every 30 seconds. Can take up some bandwidth, can take a lot of time. If you go, 4 or 5 or 6 routers down the line in a bus sort of arrangement, it can take several minutes before a route update gets to the far end. Several minutes is an eternity in routing, in networks in general. EIGRP, if you have all Cisco devices, is the protocol of choice, even though it's kind of a pain because this is the one we're going to introduce wildcard masks. OSPF is a standards-based, so if you have different manufacturers, you can use OSPF. If you have all Cisco, EIGRP probably is the way you're going to want to go. The objectives, enhanced IGRP. He spends in these slides some time talking about how you make IGRP and EIGRP work together. I'm going to go through those relatively quickly because IGRP is not even on the new Cisco routers. If you have routers with IGRP, just know that they work together. They use the same basic configurations. They use the same basic let's share route information, and they automatically do something that we'll look at called redistribution. Redistribution says that this autonomous system, term that we've talked about, and EIGRP uses autonomous systems. Autonomous systems mean that they only share information among themselves, the ones that are the same, that are members of the same autonomous system. We can force those things to share information. If IGRP and EIGRP are configured with the same autonomous system, they automatically share the routing information. So if you've got some old routers and some new routers and you're using this protocol, Cisco routers obviously, you can use both protocols until you can get the network upgraded. Verifying EIGRP and configuring EIGRP, we'll look at that. I've got one set up to do an example that we'll go through, show some, hopefully some things about it, some oddities about it, not really oddities, but maybe a little bit of unusual things about it. Open shortest path first, OSPF, we'll look at configuring, verifying, configuring it with wildcards, OSPF with wildcards. So we're going to use wildcards for these routing protocols. And wildcards, again, nothing dramatic about wildcards. They're just subnet masks in reverse. If you, and Dustin said you turn zeros to ones, you do. Quick way, you write the subnet mask, subtract everything from a 255, 255, 255, 255, 255, subtract the subnet mask that you've calculated, you have the wildcard mask. So we'll look at those. The first slide here that I just jumped over, let me go back to it, is obviously not from his but from another one. Why do we want to use, why would you choose EIGRP? Again, EIGRP and the courses that I've taken and the things that I've read is the best routing protocol that you can use. Backup routes. What this means is that the routers themselves in a topology table, and we'll look at the tables, it's going to have 3 tables, we'll look at the tables in a minute. In a topology table keeps all of the information that it's learned. It's kind of like on your GPS. If you're going down the road and you don't take a turn, what happens immediately after you don't take the turn? You get a new route, and you get it relatively quickly. That actually goes through a recalculation, which is what OSPF does. This thing remembers the backup route so that if one goes down, it says, oh, I've got the backup right here. So it keeps backup routes. None of the other topologies do that. They have to go back and recalculate. Something happens in RIP, it goes back through the whole convergence again. OSPF, even though it probably could keep these things, goes back and recalculates, and every router in OSPF recalculates the best route. Has all of the information, is kind of like Google Earth when you can see everything, see all the streets and all the other good stuff. If you ask it for a route, it'll give you a route based on your definition, shortest time, no interstates, whatever else. But every time something happens in OSPF, it has to recalculate. EIGRP does not have to recalculate. So it's going to be quicker to converge. Simple configuration, it is simple configuration, very much like RIP. And router RIP was really easy, right? Router RIP and then whatever networks we wanted. We didn't have to worry about a subnet mask because RIP is classful. Flexibility and summarization. And summarization, when you hear the term summarization in Cisco, think SuperNet. And again, why we want a SuperNet? What I'm going to try to do, and I'll put some more on, is put a bunch of interfaces. The way that you can, when you're practicing learning about routers, the way to make a whole lot of routes available with having a whole lot of routers is to use loopback addresses. You can put loopback interfaces on by just typing INT, and I'll show you INT space LO, whatever you want the loopback number to be, LO1 through a whole bunch. And then you can have a whole lot of networks. And then you kind of get an idea about what summarization does for you. Instead of typing IP or network, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you type it and then the wildcard mask that will summarize that. This protocol allows you to do summarization on any interface. OSPF is not going to do that. And oh, by the way, one of the oddities about it, don't know why they did it, automatic summarization is on by default. So what you've got to know is that unless you turn it off, it's going to send the classful network. It's going to summarize it to the classful boundary. Unequal cost load balancing. We talked about in RIP that if we had multiple paths that had the same metric, it would load balance. Equal cost load balance. That's why if we had a T3, we had that T3 and then the 64K, it essentially made the T3 line a 64K because it sends one on the 64K, one on the T3, and as fast as, and it can only go as fast as the slowest interface. Send one on the 64K, one on the T3. So you've now created a 64K T3 line. This one will do unequal cost load balancing so that if we have something that is twice as fast, one is twice as fast as the other, we'll send two on the twice as fast, one on the slower, two on the fast one, one on the slower. So it does unequal cost balancing. The default is equal cost. You have to do some configuration, but you can configure it to do that. Uses, again, some distance vector and some link state properties. Supports multiple network protocols. Probably not a big deal anymore because the network protocol that we use is IP. When it came out, it did IPX, AppleTalk, and all the other routable protocols. Not such a big deal now, but if you happen to get into an environment that has those protocols, it's available to you. Enhanced EIGRP, and this is the rapid convergence, reduced bandwidth usage, multiple network layer support. Uses, and this is a term you'll see, dual diffused update algorithm. This is just what it uses to calculate the routes. This is what makes it available to keep the backup routes. Just like when we get an OSPF, the algorithm that it uses is shortest path first. So dual is the algorithm, diffused update algorithm. To select Loop-free routes and enable fast convergence. Loop-free routes is a big deal, which means that we could have multiple paths, but it's only going to pick the loop-free paths. Up to 6 unequal paths to a remote network, 4 again by default, and I think that was the same for Ripple, and 4 by default, and up to 6 unequal paths. So that means that if we had a backup going out of our location to someplace else, instead of having it sit there just to be a standby router, we could actually use that router. And if the other one went down, it would then obviously become the route of choice. EIGRP and IGRP, you can look in the book what he talks about. Similar metrics, same load balancing, improved convergence time with EIGRP. Reduced network overhead, maximum hop count of 255 is 100 by default, and RIP was a maximum hop count of 15. 16 became infinity, so this one will go further. Can differentiate between internal and external routes, and I'm going to try to demonstrate that. Internal and external routes means that internal routes are in its own autonomous system. External routes come from someplace else. When you get internal and external routes, the administrative distance is different. The administrative distance for internal EIGRP is 90, and the administrative distance for external EIGRP is 170, I believe, which means that the ones that you get from outside the organization are not as trusted as the ones that it shares among itself. And again, administrative distance is trustworthiness, believability of the routes. 0 is, quick review, 0 is directly connected, 1 static, 120 is RIP, all right, 90 is EIGRP, and 110 is OSPF, does that sound right? The reason that's important is which protocol is going to be used first. Can we have multiple protocols running on a router? Yes. Are all of the routes going to be on the router? Yes. Is it going to show you all of the routes? No, it's only going to show you the one with the best administrative distance. Can we use, and we'll look at a simple redistribution. We'll make a couple of autonomous systems in the demo part and show redistribution. And again, it's not a real dramatic thing to do. No updates. RIP broadcast every 30 seconds. RIP v2 multicast every 30 seconds. EIGRP uses a multicast 224.0010 when there is a change to the routing topology. If a route goes down, it sends the changes, and only sends the changes, not the entire update, because all the routers have the whole topology. And if you think about that one, that statement, all the routers have all of the topology and are able to do the calculations, that means that you need a more powerful machine to do that. Newer machine takes more processing power to run these two routing protocols. Are they used a lot? Probably now, because the routers are more and more powerful. But as we go through these things, what do you need in your environment? If we've only got a couple of routes, static works just fine, and we don't have changes. Static works just fine. If we've got 200 or 300 routers, not so much. 200 or 300 routers, RIP probably wouldn't work so well, would it? 200 or 300 routers, and they're all Cisco, EIGRP would probably be a good idea because it's proprietary. 200 or 300 routers, and we're going to put in some 3coms and some Ciscos and some HPs. Then we're going to have to go to OSPF, which is the one we'll talk about next. Hello messages are sent every 5 seconds. That sounds like a lot of traffic, doesn't it? Every 5 seconds. And the hold time for this is 15 seconds, or they call it dead timer. 60 seconds on most WANs. The hello messages every 5 seconds are multi-access networks. Multi-access networks, think Ethernet. Means that we have a lot of routers talking together. WAN are going to be point to point, so you don't need to send the information as frequently in a WAN because it can only go one place. So WAN's normally every 60 seconds, multi-access every 5 seconds. The dead timer, is hold time's what we call it in RIP. The dead timer, 15 seconds, which means that if it gets below 15 seconds, it considers the route no good anymore. Then we'll go into the update cycle. But update only if there are changes in the topology. The hello messages are just sent to the guy next door and said, hello, you still there, basically. Hello, hello. There's some other information goes in, which is what's the last time you got the update, those kinds of things. But hello messages are just kind of like little pings. Maybe it's like if you're sitting next to somebody in a class, you want to nudge them every once in a while, be sure they're awake, right? The hello message, I'm still here, and that's all those messages are. So even though it looks like a lot when we say every 5 seconds, it's really not a lot of bandwidth because there's not much in the packets that it sends. The terminology, we've got 3 tables: the neighbor table, the topology table, and the routing table. The neighbor table is the hellos. When an EIGRP router comes up, it sends hello messages. Just sends hello messages out the multicast address, to the multicast address. See if there are any other EIGRP routers around. Anybody else speak EIGRP? If there are, then they'll answer them. Then they'll know about the neighbors, and they will then, and it kind of becomes, when we talk about this, we talk about it has the properties of a link state protocol and the properties of a distance vector protocol. The neighbors tell you about all the stuff that it knows about. So you get that information from them. You don't, well, that's not true. I'm in OSPF. The autonomous system everybody talks about. So we have the neighbor table, the next hop router, and the interface. And in this protocol, just like in RIP, you have to include the interfaces in the autonomous system, because when we do the network advertisement, that's the thing that tells it to activate EIGRP on that interface. The topology table lists the destinations, and a couple of terms here are successor and feasible successor. And I guess one of the things to think about successor, and I think he says in the book, think successor as successful. That's the one you're going to use. A feasible successor is the backup route. It's kept in the topology table. So this thing keeps all the routes there. It keeps the best route, the successor route, and the successor route's the one that's going to go in the routing table. If something happens to the successor route, we have the feasible successor says, oh yeah, okay, that one's down. I know, next man up, kind of like these football teams when players go down. Who's next? Well, the successor, the successful route goes down. What's next? What's the next available route? It's already in the topology table, is moved into the routing table. It doesn't have to go through all the calculations, all of the sharing, all of the, oh, something happened, now let's just share all the information again. OSPF has the information, but it has to recalculate the best routes, the shortest route, if something happens to the system. So neighbor table, the neighbors, the other OSPF routers, and we'll look at those when we do the demo that we're talking to. The topology table based on the information that's learned from the neighbors. And then the successor goes into the route table. The successor, the successful, the best route that's available. Neighbor table and topology table are held in RAM and are maintained through the use of hello and update packets. So anything that's held in RAM is going to be quicker, but anything that's held in RAM means that we need a more powerful machine with more memory in it. So that's one of the reasons that as we go through this thing, why do we have the different protocols? Depends on your equipment, depends on how many routers you have, how big is your network. I mean, would you want to try to maintain a static route with 100 routers? Would you want to try to maintain a network with 100 routers using a RIP? What happens if anything changes? I mean, you could be waiting for several minutes as the management's jumping up and down, what's the matter with the network, while you're trying to get things fixed. Successor routes used by EIGRP to forward traffic to the destination. Again, the successor, the best route, goes into the routing table. The backup routes are held in the topology table for use if they're required. Successor routes are stored in both the topology table and the routing table. Obviously, the successful ones we want to send to the routing table. The others are there in case. It's a composite metric to pick the best path, and I think we've already talked about this, based on bandwidth and delay. Delay is the packet delay. So it kind of monitors what's going on the network to find the best path. Bandwidth's going to be the primary one, and this just shows the multi-protocols, IP, AppleTalk, and IPX. AppleTalk and IPX not really used anymore. IP is the protocol that we use. Can load balance across 6 unequal costs. We've already talked about that. The default is 4. You have to tell it, and the command is variance. And if you use something like a variance of 2, it says, oh, I'll use the best path in something that's 2 times worse. And I think you can go up to something like a variance of like 999. So you can have really wide differences in the bandwidths that you're talking about for these things. Configuring it, and this one is pretty simple. Enable EIGRP router. We're in the router config mode, router EIGRP. The 10's the autonomous system number. Autonomous systems, if we have EIGRP 10 and EIGRP 11, EIGRP 10 doesn't talk to EIGRP 11. That's what we'd have to do the redistribution. It's just like room 111 is not talking to the people that are in room 109 on the other side of the wall. But you can share information in the room because you're all in the same autonomous system together. And then we advertise the networks, 10.0.0.0. If you have, you can advertise these things, and again, it does, by default, does an auto summary if we want to not advertise everything. It's kind of interesting. You type the network number, and you can type the address of the interface, and we'll do that, and the wildcard mask, and it will automatically determine what the network address is for you. So it's not like that you've got to go back and every time determine the network address. Don't know that I would try that on a cert test, but when you're actually doing the configurations, you don't have to go back and make that exact determination, and we'll do some of that. Just see if I lied to you. Redistribution is a command that allows us to have, and this says IGRP and EIGRP. Now, I think this is automatic. What it does is takes the IGRP routes and advertises them in EIGRP. What I want to do when we do this thing is have a couple of different autonomous systems, because autonomous systems only talk to themselves. They only talk amongst themselves. They're clicky. What if we wanted to share those routes? Then we would use the redistribution command. What you do is go into the protocol that you want it sent to. If I go into router EIGRP 10, and then the command would be redistribute, and if it was an OSPF, and then I would have to put the metrics in, because each of these things have different metrics. This one uses a really big number, bandwidth and delay, and if you look at the calculation, you don't really want to know how it gets to that number, because it's a pretty extensive mathematical calculation, but it's based on bandwidth and delay. It's a combination metric. OSPF uses cost, which is basically how fast are the interfaces. And Ethernet's got a cost of 10 maybe, and a fast Ethernet a cost of 1. And they've redone those things, because when they had the original cost, there was no gigabit. And if you didn't redo the cost, then gigabit had the same cost as fast Ethernet, which wasn't so very good. And that uses the lowest cost. So redistribution, we can send routes and we can redistribute static routes. We talked about in RIP that static routes are not advertised. Static routes are not advertised by default. If we want them advertised, redistribution. And redistribution is not part of CCNA. It's part of CCNP, but you really need to know about it if you've got multiple protocols running on your network, that you can do that. You don't have to try to put everything in the same way. And that may or may not happen to you. The default path, assuming the default parameters, which one's RIP going to take? The 56K, even though we have all these really much faster systems here. Which will EIGRP take? All of them. By default, it will take the fastest one. Equal load balancing, equal costs. Bandwidth and delay, the 100 base was going to be faster than the other ones. We can configure it for unequal cost balancing, so we can, yes, make it use all of them by using the variance command, telling it to send information. So it would send maybe 1 on the 56K for every 10 on the 100 base, and maybe, 10, 100 base, 1.544, 100 megabits per second. Very few over these others, and then most of the traffic's going to go on the 100 base. But you can use those in the load balancing. And I think this kind of gives you an idea about the 100 base, 10 base, 100 base, those kinds of things. I don't know why you didn't put 100 here, but how much more bandwidth you get out of a LAN than you typically get out of a WAN. How many packets would go across one if it was 10 base, and one here would be 10 on the 100 base for every 1 on the T1, and maybe for every 0.6 or 0.3 or 0.2 on the 56K. Not very many are going to go on the 56K if we balance it. And if we didn't put it within the percentage parameter, it might exclude the 56K. Depends on what you use in the variance command. The variances, again, if we did a variance 2, it said use the fastest one and something that's twice as bad. A variance 2 wouldn't do that, would it? We need like a variance 10, because 10 times worst, 1.544, just for round numbers, we'll use 1. 1 here, 1 times 10 will give me up to my 10, so we would use both. We would send 10 on the fast one for every 1 that we sent on the T1, but we would be using both of them. The EIGRP operations show IP EIGRP neighbors. To be sure that you're actually talking to somebody and who you're talking to, who are your neighbors. Show the topology, displays the topology table so that you can see what's in there. Do you have backup routes? What are the backup routes? Show IP route EIGRP displays the current entries in the routing table for EIGRP. Show IP route, or show them all. EIGRP, the symbol that represents it's going to be a D. E was taken when they started doing the letters, so EIGRP is D. RIP was R. OSPF is going to be O. EGP, exterior, which is not listed in the table anymore, used to be E. Show IP protocol shows us what's running, and we'll take a look at that. What's running and what autonomous systems are running on that particular router if we have multiple autonomous systems. If we have more than one protocol, it's going to show us all of the protocols. Show IP EIGRP traffic displays a number of packets sent and received. Are we actually sharing information? Is the protocol working? The show IP route, again, D are going to be OS or EIGRP. I'm trying to do OSPF. I don't know why. EIGRP routes 90, and then the metric 2172. Directly connected, says directly connected, and the administrative distance is going to be 0 of this one. And again, here the D, the EIGRP, administrative distance of 90, metric 2681, connected, and then 90, 2707 via the next hop address. And then it tells us the serial port that it's going out of also. If one of these went down, it would look for the same administrative distance and the next best metric. These things have the feasible distance and the reported distance. It's called a reported distance. The reported distance, and I think that's the term they use, the reported distance is from the next guy. The distance from you is the feasible distance, which we're going to get the metric from. For a route to be considered a feasible successor, the distance from the next guy has got to be within the parameters of the feasible distance. it has to be less than. You've got a question in the network, which are the feasible distances, and feasible distance, which are the backup successor, feasible successor. And it has to do with if it's too great, if the feasible successor's distance is greater than the advertised distance, then it's not going to work. D is for dual, so D is used in this thing. Administrative distance and the cost, we've already talked about that. So let's stop here and do a little demo. Okay, so we have a little topology here, not anything really dramatic about it. We just want to share routes. And I've used the Ethernets because they were easier to do. These don't have any real configurations on them. Some of them I have put in. If I can spell. This one just has its addresses, 192, 168, and it's manual up. So it's connected, doesn't really have anything in it. This one's got some loopback interfaces on it. Again, loopback interfaces when you're doing things, you want to create a lot of networks, and you don't want to have a lot of routers. Just put in loopback interfaces. To make a loopback interface, go to config T, INT, oh, wait a minute, got to spell it right, no, Control Shift 6 to get out of there. Config T, INT, LO, and the next one would be 4. IP address 192.168 dot. Let's do 34 since that would be the next one. And you put addresses on, not network addresses on. Show. So we just created another network. If we go into the show IP route, spelled correctly, then we have all these directly connected interfaces. Many of them are loopbacks, and they have addresses. So you can actually use those to do configurations with, to practice with, to do summarizations with, as we do those things. But in this case, let's configure EIGRP. We're on router 3 here. And let's configure it into an autonomous system. And let's use 2 autonomous systems on this thing, just so that we can then do our redistribution on it from one to the other one. So config T, router, EIGRP, and then we have to put, if we do the question mark, tells us the autonomous system number 1 to 65,535. So you can have a lot of them. Hopefully you wouldn't have that many. But let's use 10, and it doesn't matter which you pick, but the one you pick has to be the same on all the routers that you want to share that information on. So we'll do these things here. So router EIGRP 10. And now then, I got to see which interfaces are which. That didn't do me a lot of good. Options, preferences. Always show port labels. And now then, Fast Ethernet 00 is the 1.3, so this is the one network over here. And let's see if the little thing that we talked about. So we're going to use network 192.1.16. I guess if I use a dot it would work better, right? .168.1.0. Since this is classful, I don't really need to put a mask in there. I could. This should now share all of the .1 information on that's available. The rest of them, though, are not .1s, are they? The 2.2 went to the other network. I don't want to send this information out that network. So I won't activate it for this autonomous system. I'm in autonomous system 10. I've got a network 192.168.1, whatever it was, 3 I think on this one, and then 192.168.2, whatever it is. I don't want to share the autonomous system 10 on the 2 network. We're going to build its own autonomous system, and then we'll redistribute from one to the other one. So let's pick another network. Let's pick a couple of them. Let's use the 30 and maybe the 32 network here. Should I have any neighbors yet? The command show IP EIGRP, and again I recommend the tab key. That's what I was using. That's why I can type so fast here. No neighbors, and we wouldn't expect any neighbors, would we? Because we hadn't configured anybody else to talk to us. So can we configure somebody to talk to us? Let's see if we can do that. So let's see if we can make this guy over here talk to us. Fast Ethernet 192.16. I did that wrong, didn't I? Was that 168 or 16? I got this one configured wrong. Is this one going to work? Probably not. Let's go to some of these others. I'm pretty sure are right. One 192.168.11. So I should now be able to go in here and config T and router EIGRP, and we use 10, right? Network 92.168.1. Let's try this. .1.1. See, I didn't put the network address in. I put 1.1, which is its interface, and it now says that I have an EIGRP neighbor. It immediately comes up, and it is pretty quick. And we have the 2 routes to the 30 and to the 32 network from this guy. So we have shared that information. I had to put that interface on it before it would activate EIGRP. Let's see if router 5 has anything. So we got some routes here. So we can go in here and router EIGRP 10. Config T would help, wouldn't it? Network 192.168.1.5. Adjacency immediately goes up. I can now share my other ones, which are 192.168.50, 192.168.50.0, or I could put the 50.1 address in here, and the 52 address in here, and the 53 address in here. It now knows about using the EIGRP, the Ds, the 30, the 2 that we advertise. What we need to do is go to router 3 or one of these other routers. Let's go to router 3. That's the one that had. And it has a whole bunch of routes on it. EIGRP and connected routes. What we wanted to do was put another autonomous system on this thing and see if the autonomous systems will share the information between each other. And my guess is not yet. So let's do, which networks did we share here? Do you remember? You were supposed to help me with that. So we shared 30 and 32. Router EIGRP, let's say 50. The do command really is handy. So I use 30 and 32, so I got 33 and 34, huh? Dot 33.0 and 34. But I didn't get any, oh, I'm ready to talk. What else do I have to share? The interface address. Because when we share that information, we put that network statement in the EIGRP, it says activate it on this interface. So now we need to use 2.1. Let's look at the IP protocols. It says that we have EIGRP 10, which is sharing 30, 32, and 1. The routing information sources 1.1 and 1.5. Those would be our neighbors, right? We're getting other information from. And we also have EIGRP 50, and it's sharing the 33, 34, and the 2 network. And it doesn't have any neighbors yet, because we haven't given it any neighbors yet, have we? So now let's go up here to this guy. IP route, we have a couple here. We got 168s, 102s. So we want to go to config T, router EIGRP 50, right? Network 92.168.1.02.0. How come I don't have a neighbor yet? I turned on OSPF, or OSPF EIGRP. Why don't I have a neighbor yet? I didn't see anything say I had a neighbor, did you? Huh? God, I gave an autonomous number 50. Why don't I have a neighbor yet? No, I didn't put the network address of the interface that I want to do the EIGRP conversations on. So now I need to put in what the 2.0 network. Now I have a neighbor. Who is this neighbor? What networks do you think this neighbor's getting? I wish I could spell route. It's getting the 33 and the 34. We're not getting the other networks that are available out there. We're only sharing the information on this particular network. If we wanted to send the 50 routes into the EIGRP 10, we would go back to the router that has them both here, and we have the adjacencies. This guy ought to have everything, and he does have everything, doesn't he? Because it has both autonomous systems running on it. What if we wanted to not have the autonomous system someplace else? If we had more than that, we wanted to share some of them in one but not in the other one. We should be able to go down here and do a config T, router EIGRP 10, and redistribute EIGRP, and then the autonomous system number. If we were redistributing it into something else, we would, like into OSPF, we'd need to put them out. There are default metrics. A couple of them have default metrics of infinity, which don't do you a whole lot of good. But right now I'm just going to try with the enter key. And now with any luck, when I go to router 2, for instance, oh, it's the one that had, we had to pick the one that had the wrong network address, didn't I? We now have a bunch of them, and some of them come up as EX. If you look at this thing, D, dual, or IGRP, EX. EX is an external EIGRP route, came from a different autonomous system, was redistributed into it. And the metric for it is 170. So it's not as trustworthy. For instance, if we had the same route using OSPF internally, it would use the internal OSPF route because 170 is not as trustworthy a route. So we covered a couple of things here. One, how to do it. Not a big deal. I think it's kind of useful, I won't say interesting, but useful that when you do the advertisement of the interfaces, you don't have to necessarily have determined the wildcard mask of the interface itself. If you want to limit what's being advertised, you need to do that. And you can do that. We could have used the 192.168.1.1 if we had subnetted it and used a wildcard mask of 0.0.0.3 if we had subnetted it with a 255.255.255.252 mask. And again, to get the wildcard, subtract the subnet mask from 255.255.255.255. What wildcard masks really do is it says zeros. If it's a 0, it says check this to see if it's what it says it is. If it's a 1, I don't care. Anything that's got a 1 in it can go. Are there questions right now? I'd like to take a break here quickly, and then we'll do OSPF, and then we'll get into the rest of the business of the day. Questions? Okay, let's take a break. Okay, what we're going to do now is talk for a few minutes about OSPF, introducing OSPF, and each of these protocols that we're talking about obviously have more configurations that you can do. If you want to get into those, do the CCNP route course because they go into some extensive configurations of both of these protocols. So OSPF, unlike EIGRP, is an open standard, uses the shortest path first algorithm that was developed by a guy named Dijkstra. Link state routing protocol versus the distance vector can be used to route between autonomous systems. What we're going to have in this thing is areas, and the CCNA objective is configuration of a single area OSPF network, which is really not all that complex to do. And the single area number, the area number has to be 0. Area 0 has to be the first area that you configure. It's considered a backbone network. A hierarchical structure, area 0, area 1, and area 2, and much like the autonomous systems in EIGRP, the areas only share information within themselves, and they're going to have inside of them things called designated routers and backup designated routers, the mouthpieces. And when we go between areas, we're going to have area border routers, and they're going to talk from area to area. They're going to be the relays from those things. Consists of areas and autonomous systems, minimizes routing, update traffic, supports VLSM, unlimited hop count in this thing. These areas, and again, the CCNA only requires a single area configuration. The advantage of this protocol is if you have lots of different areas, individually managed systems, and you want to put the networks together. Whereas EIGRP could summarize, you can summarize any place you want in EIGRP on any interface. In this system in OSPF, summaries happen on the area border routers, the routers that go between, or the routers that go between different areas. And what you want to do in these areas to make this more efficient is to use a hierarchical approach to your networks that are in there, networks that are in there. Hierarchical approach meaning that we would be able to supernet so that we don't have, if we have 100 routers out here, so that we don't have 100 routes in the area border routers. We have a single route, a summarized route. So this thing does summarize auto-summarization. It does auto-summarization, and it summarizes on the area border routers, not on the individual routers. within the system. Link state, common view of the entire topology. So it's going to have the entire picture. But unlike EIGRP, it's not going to have backup routes. It's got the topology table. We talked about the topology table in EIGRP, which is, it has the routes already pre-calculated. This would be much like, and I keep talking about Google Earth, if you took the Google Earth picture and you saw everything that's there. And you move into an area, and you're going to find the route to the mall and the route to the grocery store and a route, to the kids' school or whatever else. You're going to pick the shortest path, and that's what this thing does, or what you perceive as the shortest path. This thing takes the entire topology of the network, has to build the topology of the network, stores the topology of the network, and determines based on the cost of the links what the best path is. So this uses cost, which is basically, 10 base, 100 base, gigabit arrange, and each of the link speeds has a cost assigned to it. If a route goes down, unlike EIGRP, which has the backup, it says, here I go, here you are, then it goes through the calculation again. It has to do the recalculation to find the shortest paths that are available. Calculates the shortest path using the shortest path first algorithm. It is event-triggered updates. It's not going to be a broadcast or a multicast like RIP was, EIGRP wasn't. These things only send information when something changes. Well, except for the hello message that says, oh, I'm still here. This one also uses, within an area, a multi-access area, designated routers and backup designated routers. The designated router, instead of all of the routers talking to everybody, if we had 100 routers and 100 routers talking to 100 routers, they all talk to the designated router, which takes the information and then it sends it to all of the other ones. Kind of minimizes the traffic that way. And the backup designated routers are in case the designated router goes down. Can be used between autonomous systems. Backbone internal routers is backbone area, and again, area 0 has to be the first area that's configured, the backbone area. And all the other areas must connect to area 0. If you really want to figure out how to not do that, do the CCNP route course. You can do that, but you have to tunnel between the area that it's not attached to. So for our purposes, all of the other areas have to be attached to area 0. Area 0 is the backbone area. The routers between the areas are border routers, area border routers. ASBR would go from a backbone, it says to internal routers, and this one goes to internal routers. The ASBR actually goes to different protocols. It might go to your ISP, area system border routers, and the backbone. To configure them, it's not all that much different than all the other ones we've looked at. Router OSPF, process ID is only significant on the router itself. Unlike the autonomous systems on EIGRP, which had to be the same, the process ID does not have to be the same. The area has to be the same for it to share the information. So it defines the OSPF as an IP routing protocol. The process is locally significance needed to identify the unique instance of an OSPF database. Network address, mask, area number, the area ID, the mask here, so network mask, the network address, the mask, and the area ID, area 0 has to be the first one. If we have other areas, then you would use that area. And the area ID has to go on each line. If you do these things, and when you put them in the first time, use the up arrow key, just go back. If they're all in the same area, just change the network address. On this one, routers 1, 2, and 3, area 0. On all of these things, host name, router 3, router OSPF 10, the process, and this one's 2 is router OSPF 20, and One is router OSPF 30, doesn't matter. Process ID is only significant to the computer. It just tells the computer, the router, tells the router which instance where to look for that process. Network 10.1.2.3 tells it to advertise that specific interface, 0.0.0, wildcard mask. And it's going to advertise it into area 0, which means it's only going to advertise the 10.1.2.3, the 0.0.0, it's only going to advertise that network, not the entire network. 10.1.3.1, 0.0.0 on area 1. So it's going to advertise both of these networks in area 0, OSPF area 0. And this one, network 10.0, 0.255, this one says that it's going to advertise all of the 10 networks, 0.255.255.255. The 0 means to check the 10, going to advertise the 10, anything else we don't care. It can be 10 dot anything, and it'll advertise it off of that router. This one, network 10.1.0.0, 0.0, it's going to advertise all of the 10.1 networks. Because it's 0.0. I care about the 10, I care about the 1, I don't care about the last 2 octets. That's what the 255s mean. Don't care. Put anything in there you want. 10.1.3, 10.1.4, 10.1.6, 10.1.200, it will advertise all of those. Area 0, 10.5.5.1, 0.0.0 is going to advertise the 10.5.5 network to area 0. So the configuration, again, is basically the same as everything else. Syntax is a little different because you have to have an area number. You have to tell which area that route goes into. Verifying it, show IP protocols, same as we've had before. Tells you which protocols are running on the router. Show IP route, same thing. Show IP OSPF interface is going to show you the interfaces that OSPF is using. Show IP OSPF neighbor. Who are your OSPF neighbors? What this is going to have is a router ID. The router ID is the interface with the highest IP address. That address becomes a router ID. So when you see router ID and it's got an IP address, not necessarily the address it's talking to, it is the highest IP address, and they use the router IDs when they're calculating the designated routers and the backup designated routers. If you put a loopback interface on, the loopback interfaces trump physical interfaces. So if we had a physical interface that was 1.1.1.1, we'll use simple ones, and then I put a loopback interface that was 2.2.2.2, then the router ID would be 2.2.2.2 because that would be the higher IP address. If I really want to dictate it and not worry about the IP addresses, I can use the router ID command. Router ID and then 1.1.1.1, 2.2.2, whatever you want to use for those things. So you can force the issue. The thing that might happen to you is you just don't do anything. You use the highest IP address on the physical interface. What happens if you change the IP address? Then the router ID is going to change. Then all of the other OSPF information may change. And the problem becomes it only changes if you restart the processes or restart the router. So you change an IP address today, and in 6 months you restart the router, and all of a sudden all your OSPF stuff quits because the router ID changed. And now these things, other things that you have configured that you use the router ID for, don't know who to talk to. The router ID command is the safe way to do that so that you configure the router IDs when you start. That way they'll never change the IP addresses or anything else. But that's one of the issues is you can make a change today and it doesn't really take effect until, next year when something changes. This one uses hello packets to create adjacencies and maintain connectivity with neighbors. Adjacency is just kind of like neighbors. It's kind of like the autonomous system neighbors. Adjacencies are routers that know about each other. Hello packets provide dynamic neighbor discovery maintain neighbor relationships. Yes, I'm still here. And hello packets and link state algorithms from other neighbors help build and maintain the file of the topological database, because we're getting information from these other routers. Remember, we're building the entire topological, the entire topology of the network and maintaining it on that router. So that should tell you, oh, again, a more powerful router. We're going to have something that supports this. It's going to take more memory, more processing to do it. But large network, you probably want a large network. We can break it up into areas, and then we can share the information between the areas. OSPF uses multicast address 224.0.0.5. That's the one that says anybody there. We're also going to have other routers that's going to answer it, and the routers, will answer on a different address. Area border routers, DR, non-DR, and BDR. Each of these things, the DRs and the BDRs, are based upon the router ID. The non-DR is just another router, because we only need one DR designated router, one backup designated router. The area border router will go to a different area. They don't show another area here. But these guys all establish a relationship. And this is in an environment that has multi-access again. If we only have two routers, a serial interface, we don't need a designated router and a backup designated router, because there's only two routers involved. The designated and the backup designated are for multi-access, for a multi-access environment. Again, think Ethernet for those arrangements. The router ID I already talked about needs to be uniquely identified to properly arrange them in neighbor tables, and we'll look at those when we do the configuration example. Multicast hellos are sent compared. The router with the highest priority is elected to DR, and by default, they all have the same priority, 1. The one with the next highest priority is elected to BDR. You can change the priority with the priority command. So priorities will take precedence over router IDs. The one with the highest priority is the designated router. The other one is the backup designated router. And that goes back, we make a change today, reboot the router in 6 months, and all of a sudden the whole topology, who's talking to whom, has changed. OSPF sends hellos, which elect the DRs and the BDRs. The router form adjacencies with DRs and BDRs in a multi-access environment. So they don't, after we have the election, they don't all talk to each other. They talk to the DR and the BDR. Designated router is the one that you would send your changes to. It then sends the changes to all the other routers. Configuring the loopback address, and we've looked at that, not in the OSPF table. Unadvertised loopback address advertises loopback addresses. The router ID is the number which is known to OSPF, and again, we'll look at that. And the router ID is going to be, by default, the highest, the IP address, the highest IP address on the physical interface. If we configure a loopback address, then it'll be the one with the highest loopback address. If we use the router ID command, it'll be whatever we put in there. The router ID command overrides, preempts all of the other things. Default, the highest IP address on the active can overridden by a loopback interface. IP address called the logical interface, also by the router ID command. Show IP OSPF interface, Ethernet 0. Ethernet 0 is up. Line protocol is up. That's what we want to see, right? Up, up. Internet address 192.168.1.137/29. This is in area 4. So it's a 29-bit subnet mask /29. Process ID, only significant to the router itself, is 19. The router ID 192.168.1.137, which is this address. Network type is broadcast, which means it's going to be an Ethernet type broadcast, or an Ethernet type address. We have a non-broadcast multi-access frame relay, and we'll do frame relay in the next block. Cost is 10. Transmit delay is 1 second. State, this is a DR. priority is 1, and again, all of them by default have a priority of 1. And we're going to use the highest priority. So if you wanted to change it, you could do a priority of 50 if you wanted this one to be the DR. Designated router ID is me. The interface address is the one that we have configured on this interface. No backup designated router on this network, which means it's probably the only OSPF router on the network. Otherwise, one would be elected. You can tell a system that it's never, ever, ever going to be one of these by making its priority 0. If you make the priority of the router 0, it doesn't participate. It doesn't run for election. So it can never be one of those things. Timer intervals configured to hellos 10 seconds, the dead 40, wait 40, retransmit 5. The dead timer is how long the systems will wait to presume that the router is no longer participating, and it'll take all the routes out. And then the hello due in every 10 seconds. This one is due in 6 seconds when it gets to the 0, and if it doesn't have one, if we go through 4 cycles, then the dead timer comes up and says, "Ah, this guy's not talking to me anymore. I presume he's not there." Last flood. Neighbor count is whatever. What options can you configure that will ensure R2 will be the DR of the LAN segment? We could configure it with a loopback address. We could configure it with a router ID. Or we could configure the IP address on the interfaces. That's not a good way to do it by changing the IP address. You really just put a loopback in, or probably even better, easier, use the router ID command to make it work. Wildcards, we've already talked about these. 0 means exactly, and if we use 0.0.0.0, it means that specific address. 0.0.255, 0.0.0.255 is a class C, any class C. We don't care about what's in the last octet, only what's in the first 3 octets. And the block sizes, he's big on block sizes, and these are kind of useful. And if you had these things, the 30 bits of 255, 255, 252, if you subtract all of that subnet mask from 255, you're going to get 0.0.0.3, the only one that, in the end, 255 minus 252 is 3. So if you have trouble with these things and you can get the subnet mask, just subtract the subnet mask from 255, 255, 255, 255. And that'll give you the wildcard mask. That'd be router, the wildcard masks. I guess well, E0, 192, 168.30. The wildcard mask is going to be, with a 24-bit, the wildcard mask is going to be 0.0.0.255. The 30 bit's going to be 00. The wildcard mask will be 0.0.0.3. So with that, let's see if I can stumble through an OSPF configuration for you. So let's use the same topology here, and we're not going to use this router. Let me get rid of that router because he has the wrong network address, right? So when we go into this thing, what do we need to configure OSPF? Need to be in enable mode, right? One of the things that I personally find kind of handy before you start doing these things is do a show IP route. I'll tell you everything that's there. But the other thing that I'm still going to have to know is, what's my directly connected interface? That doesn't show there, does it? Yeah, it does too, 192.168.1. So these are all of my interfaces, and I have these. So the config T, and the command was router OSPF, and then we put the process ID. Does it matter what the process ID is? Now, but typically what people will do is use the same one on all the routers. It doesn't matter, but that's just the easiest thing to do. And then we need network commands, right? A, B, C, D, so let's do 192.168.1.0 and to 255, so We need the wildcard mask, and if I just try to do an enter here, it says it's an incomplete command. So I've got to put something else in here. And I need to put the wildcard mask as what, 0.0.0.255. No, I still have an incomplete command. Because what do I need now? Question mark will tell us, right? We need an area number. So let's be area 0. And network, well, I got 50. Let's just advertise all of these guys here. 50, area 0, 52, area 0, and 53, area 0. Shouldn't have anything yet, right? Because I don't have OSPF running on anything else. So we can go to, I think this one had the right IP address on it. Because I forgot to do it. The do command that they added, it really is handy. I forgot to do that instead of having to go back and then come back into config, just do whatever you want. This one doesn't have anything on it except its address, but if we wanted to get that information, we have to activate OSPF on this interface. And does it matter what this one is? I'll do the same thing, but now we need network 192.168.1.0.0.0.255 area 0. What if it's doing anything? Ah, it did. We have an adjacency. Adjacency says, okay, we're talking. I should now have some OSPF routes on this thing, should I not? Think. So IP route. So I have OSPF routes, the O's. Says that 192.168.52/32 subnetted to 1 subnets. Each of them is subnetted to 1 subnets, 192.168.53.1 via 1.5, so I can get to those locations. We would hope. If I have show IP OSPF neighbor, says my neighbor ID is 192.168.53.1. The neighbor's router ID, which was the highest, in this case, loopback address on that router. And it says to get there, I go to 192.168.1.5. The state is full, and my neighbor is the designated router, the DR. So if I go, the other guy should tell us that this guy is the backup designated router, right? If I then go and add other things, this election won't happen unless I stop the processes, and the command is clear OSPF processes, and then it will go through the election again. But if I put something else on that should be the DR, it's not going to happen until something changes to the DR. So let's and the things that you can show in OSPF are the border routers, the database, the interface, the neighbors, and the virtual links. So let's look at the neighbor right now. And it says that the other guy's 192.168.1.1 because they only had one IP address. And it's a BDR, the backup designated router. Let's go put it on these other guys and see if we can make them share their information. So this one's got a bunch of them, huh? Let's got to spell it. Router OSPF 10 network 192.168.1.0 And we're still going to be in area 0, right? And we have our loading done, so we've got an adjacency formed here. Let's advertise the 2 network in area 0. Let's try something different on this other one because I think it works. It's 30, 32, 33, and 34. Do they go consecutively with something that might work with a 0.0.0 or 0.0.3.255? Can we supernet them? I don't think so. Can we? It'd be 0, 4, 8, 16, 20, 24, 28, 32 would be the next one. So that one wouldn't work out so well, would it? Network 30. Let's try this. Let me pause this. Okay, we've added that one. We're in the OSPF do show IP route. So we have 32, 33, 34, and 35. So let's see if we can then go in here and we're in the router, so we should look for the network 192.168.32.0, right? And what would it be the wildcard mask? 0.0.3.255? Is that right? Because that subnet mask is 255.255.252.0, isn't it? Area 0. Let's see if it tells me I'm crazy, and I'm not. It doesn't. So, and then we can put in that we have. That's it for the connected, right? Show IP route, and we have all of those guys. We have the OSPF routes that we're getting. That's probably enough. If we go back to this one, had a bunch of stuff on it. Then we have the adjacencies. Show IP route. We have the 32, 30, 32, 33, 34. So it advertises them, but they're still listed individually when they get there. There is a way to combine those things on the routers, but you've got to go through another step if you want to do that. So it advertised them, and I only had to put the one entry in the table of the outgoing router. If I now show IP OSPF neighbor, I get a BDR and it says a full druther. That's an other router. It's one that's not involved in the election. What if I wanted to force the election to happen? Let's see if let's see if it'll work. CLEA clear. Picked one that doesn't work. It's not programmed into this one. The clear OSPF processes. But that is the one that would force the election. If I did a shutdown, neighbor down. Something's got to happen now, doesn't it? Because I don't have the neighbor anymore. This one, BDR, now says that 192.168.53.1 is the DR, 1.1 is the BDR. So it's using, for the DR, it's using the highest IP address, and that's why the router ID, if I change the other stuff, the router ID will change those things. OSPF has lots of flexibility. If you do the CCNA, what you have to know is how to configure a single area OSPF. Then you've got some labs to do those with. Are there questions? And I'll quit, and you can start getting ready for your test. Give you time for that. Questions? No questions.